Hi everyone, I'm Maral, and today I am going to show you the steps of my project that I did in ANSYS. My project is Thermo-Mechanical FEA, a wire bonded semiconductor package. So you can see the three different modules that I use in ANSYS to do the simulation. The first one is a steady state thermal. So what you do here is that you basically put in all the temperature conditions, all the heat loads in, and you can study what are the temperatures in different layers, what is the heat flux on different layers, and you can input these as an input to the static structural. So now you will be able to study the stresses that this thermal analysis causes in the static structural mode. So here you can see the VARPs, you can see the deformation, you can see the stresses in different layers. I also decided to do a modal analysis at the very end. So here I basically did this to see how the thermal pre-stress from the CTE mismatches affect the wire bond's natural frequency that I have. So before I start, I would like to show you the geometry of what I have. This part, the part that I'm highlighting, is basically a die, a silicon die, which is typical in semiconductor packages. And then there is an epoxy layer underneath it. And at the very end, you have a substrate. The substrate, the gray, is basically is your printed circuit board. It is layers of copper and FR4 that make up your printed circuit board. And you have these gold pads on your, say, silicon and also substrate where the wire bond is connected, and you're able to read out your module. So before we start, I would like to show you the material properties. So the silicon, the epoxy, and also the gold, these all have very, their properties are known. The thermal conductivity, the Young's modulus, these are known. The FR4 or the substrate is a little bit tricky because it's actually orthotropic, meaning that the coefficient of the thermal expansion and also the Young's modulus are basically different in plane and also out of plane. So in X and Y and also in Z. And in order to get them correctly, you would need to understand how much is the thickness of your copper and how much is the thickness of your FR4 in your PCB. And then based on the properties of the copper and the properties of the FR4, you can calculate the total CTE and the Young's modulus of your PCB and the thickness of it, based on the thickness of it. So I have a little MATLAB script which basically goes through that, puts the thicknesses in, and calculates based on the area and everything, calculates the CTE and the Young's modulus in X and Y and also in Z. So after you know your properties of the material, you can add them in your engineering data. And then once you open your actually module in ANSYS, all the properties will show up here. So you will have your material here, as you can see, and their properties. Okay, and I have also imported the geometry, of course. So one thing is that the die, the epoxy, and the substrate are all 3D parts. Also the gold pads are 3D parts, but the wire bond itself, I have modeled it as a beam. So I have specified a cross section for that beam, which is 25 microns in diameter. And I have assigned the correct material selections to all of these materials. It is important for this to check the connections inside ANSYS because not all of them can automatically be generated, especially when you have a beam and a 3D element all together. So it is important to have your substrate to epoxy, substrate to gold pad, epoxy to silicon die, gold pad to silicon die, wire bond to gold pad, and wire bond to gold pad, all of these perfectly bonded, not to let anything move or slip. And then for the mesh, I have basically done the quadratic element order on all the 3D parts. And for the beam one, I am actually doing the linear one because it actually predicts it better. So for the element sizes, I have picked 50 microns, for all of the dye, the epoxy, and the pads, and I have picked 80 microns for the substrate. This is basically after starting with larger sizes and then going through the simulation and making the sizes smaller and smaller until you do not see a lot of changes, and that would be actually you're converging, your mesh is converging, and you have a good size mesh picked up. Okay, then for the steady state thermal, I have set my boundary conditions here. So I have the internal heat generation inside the silicon, and I'm looking at two cases. I'm looking at the case where after curing, I go down to room temperature, and then I'm looking at the case where after curing, I'm going down to the cold temperature. So for the cold temperature, I'm setting the bottom phase of the substrate to be -40, and for the room temperature, the bottom phase of the substrate to be 25 degrees. It is important to say that I am starting from a stress-free state, which is at 150 degrees C, and that is basically where my glue is stress-free. Everything is stress-free because that's the temperature where the glue cures. Okay, so after setting the boundary conditions here, I am also applying convection. Basically everything which is exposed except for the bottom where I'm applying the cooling has some convection going on, and then I can solve for the steady state thermal one, and I can get the temperature differences on my die and also on the different layers of my module. After that, I can input these here, imported. I can input these body temperatures inside my static structural, and there I can study how this would affect the module to warp. So the module has different layers out of different CTEs, and that's why they are going to basically contract at different rates. And that's why the whole module is going to warp. It is important for me to understand it to make sure whether the epoxy is going to hold, is the stress acceptable inside the epoxy, and whether the stress is acceptable inside the die. So the module is basically allowed to these four corners of it. Those are allowed to move in the XY plane, but not in Z. And the center of it is allowed to move in Z, but not in X and Y. And then I import the temperatures, and I get basically the total deformation and the Z deformation of the module, and you can see how much it is actually warping. You can also look at the different stresses on different materials. So for example, the silicon die, you can look at the stress of it, and you can look at the stress of the epoxy itself and see whether this is good enough to hold or not. And using this beam tool, basically you can also look at the stresses inside your wire bond. And then for the modal analysis, I am looking at the first 6 modes, basically. So here, you put the 6 modes in, and you can run the analysis, and you can get these different modal frequencies for these modes. So this is the first one, basically. You see how it is changing. This is the second one. So in ANSYS, you can ignore what it is showing here. This is not something that actually is useful. I don't know why it shows these large deformations in meters, but you can see basically the frequency which you're interested in printed out over there. And this is the 5th. And this is the 6th one. Okay, thank you so much for watching my video, and wish you a good day.